Here for a second. I want to show you something. Since it's just y'all three, and the others decided to skip school. I set up the seismometer yesterday. It's been recording earthquakes all day, which is not. These are not actual earthquakes. It's probably too sensitive, and so I don't know exactly what I need to do. I will say some of these are y'all walking around. Some of these were overnight, so I don't know exactly what was going on. I don't think there's anybody here, so it shouldn't have been being active. But like if you come back to this very first one, it was really big at first because I was touching it and moving it around, so it was kind of like all over the screen. But if we come all the way back, what happened? It just crashed. Hold on. Let's just restart it. Let it come back up. And it stores all these in files, so you can go back and look at them. I don't know if it's hour by hour or day by day, but come on. You can scroll down, I think, and it will actually move the screen up. Yeah. There's obviously a lot of stuff on here, so it's instead of scrolling smoothly, it's like blacking out. But if we come back to this very first thing right up here, which I'm almost to, I just want to get it like kind of isolated so you can see just that line and not the other lines below it. One more. There we go. So I was setting it up right here, and I went in and deleted that stuff so it wasn't like blacking out the entire screen. And then we got our first kind of line of recording. I think each line is an hour, so you can see the hours listed over here. And right here at this time, if you run the mouse over, it says it's 16:28 at the start of it, and it's actually 5 hours off. I couldn't figure out how to change the time on it because the time on my computer is right, but I guess maybe it's using a different time zone or the time code is somewhat altered. So it's actually 5 hours ahead. So instead of 16:28, it's 11:28. So I looked on my badge, and 11:28 is just before class lets out at 11:33. So about 11:28, everybody starts to get their stuff together. They're moving chairs around, they're moving desks around, and so it kind of goes off. And you can see that we have increased activity right up to like 11:39, which is just a minute after. Where are we at? 11:28. 11:39 is like a minute after class goes back after your 5 minute passing period because fifth period starts at 11:38. So this is basically like a little passing period earthquake, which is not too bad. To be fair, that could just be an assumption on my part, which is actually not true because we have a lot of other stuff going on down here. Actually, let me just go ahead and go to control settings, go to current time, and that'll take me back to where I was. But there's a lot of other stuff in here that's obviously not corresponding to y'all walking around as students. So maybe that's just a presumptuous false claim here because there wasn't anything going on like 5 or 6 hours ago overnight. The cleaning crew's not here. Who knows what this is picking up? So it could be the air cycling on. If you come around here, I actually do have it just so y'all can see on the computer screen the earthquake readouts. Come on over here. So I have it kind of isolated in here because if the air blows on it, it will get a bad reading. Come around here, let y'all see. Come. So here's it's a little. Well, this doesn't actually belong in here. It's a shelf for one of the cabinets over there. I think that's where you would sit in a chair. It's like a little desk inlet. But yeah, there's the seismometer there. I put a little cup of water in the damper so you can see the cup of water down there, I think. And it basically to kind of dampen the up and down motion to give it a little bit of resistance. You're supposed to use something a little thicker than that, but I don't want to pour oil in it. I did oil in a previous year, and it got kind of gummy and gross. And so I just decided to do water temporarily for this year. But if you like me just taking it off, yeah, you can see like it really spiked. And so this is coming like all the way up now. Just the airflow allowed to come in, and probably the airflow from me removing that caused a huge spike. And so not only is that false, but it's kind of covering up the other readings from the other hour lines. So you do have to keep it pretty isolated, but it's pretty interesting to mess around with. And so I might try and see if I can get it a little bit more isolated, or maybe move it around a little bit and see if I can get just like a baseline reading where it stays quiet like it should most of the time, and then we'll see if we can get some more information on it. But it's a cool little thing. I got it with the school's money, and so it's nice to kind of view and mess around with a little bit.
How do like actual scientists not get like fake readings with the
It's actually really hard, and so that is when I was at getting my master's at OU. One of the big things that you kind of had to deal with is determining what noise you have in a certain area, because when you're taking readings like that for oil and gas exploration, you're putting it's not that kind of seismometer, but it's like it's a different style of seismometer. You're putting them in the ground, sometimes right next to the road. Sometimes they're building or construction nearby, and all of that's going to get picked up. And so basically you have to do a lot of work of sampling and time, like observing over a long period of time to see what kind of background noise there is. You kind of input that into a computer program, and you have the computer look and kind of cancel out that background noise, almost in the same way that noise canceling headphones work. They have to have some sort of microphone on the outside to hear the outside noise that it's not putting into your ears, and then cancel that out. They give it like an opposite wave going into your ear, and so the computer does the same thing just for your seismic stuff. So it's actually really difficult, and it's like a whole different part of science. But almost anybody that does any sort of like scientific sampling has to kind of take that into account. So even like medical stuff, if you're like, let's say, testing some medication for like blood sugar levels in patients, and you give them the medication and their blood sugar goes down, that could be anything. Like, it doesn't necessarily mean it's your medication. It could be that they ate differently that day, or they exercised differently than before. And so you have to look at all the other background stuff to see if you're getting some sort of bad sample there. So yeah, it is interesting, and it kind of keeps any good scientists, it'll keep them on their toes, because I closed out my roll. I'll have to go back and do that in a little bit. It kind of keeps them on their toes, because you can never just get data and be like, that's it. This is it. You always have to be skeptical of what you have, and kind of question everything and make sure that you did all your due diligence, because someone else will come behind you and be like, no, you didn't do that right. You got to make sure you're good there. So let's start the next part. Oh, that one will wait for. All right, so we already talked about the layers. We're going to start today. We should be able to finish today with this PowerPoint with deformation. And actually, I'm going to erase this because I will need the board a little bit to do a little bit of drawing. I need to clean this board. Okay. You feel better now? I moved everybody back a little bit, so Tanner wasn't all like crowding me up here. Not that it's you. It's in previous years when we had the old desks, everybody had to get in the desk from the side, and so the desks would always migrate this way. This year, you don't have to get in, you get in from the front, and so the desks have been slowly migrating towards the front of the class. So we're good to go there. What we're starting off today with is deformation. And this is actually maybe one of the cooler things and the easier things to learn. There's lots of different types of deformation, and it's always based on some sort of strain or stress. Let me actually, real quick, grab one more thing from the closet. I have manipulatives. Is it manipulatives? I think that's the term. The educational term. The things you hold in your hand. Yeah, I thought I had it. Nice. Okay. Manipulatives. That may not be the right term. Okay. So what we have here is we're going to start to talk about deformation. We're going to start to talk about faults and folds and all sorts of stuff like that. And the first thing I want to get across is rocks can act in two ways. We're all comfortable with rocks breaking and having faults kind of like this. Like you have your rock system and you get some extension apart. When they extend apart, gravity is going to pull this one down and essentially going to slide downward. We're all comfortable with that because rocks break, and we know that rocks break, and we're fine with that. But rocks can also bend. Given the right pressure and the right type of rock and the right confining stress, they're not really going to break in the way that we think. They will actually bend and fold almost like a piece of paper or something soft. So you have like your foam here, and if I push this together, I'm going to get a bend, either up or, if I can do it right, down. And so we have lots of different types of bends, and you can actually find really, really complex rock movements underground. We took a trip not to Oklahoma, but it might have been up in Oklahoma. A lot of geology trips just involve driving on the road, and then you stop on the side of the road and look at the rocks because every once in a while you get a nice cliff face, not really in Texas. So in Texas, to see nice rocks like this, you have to go to where a road has cut through the hill. Instead of going over the hill, they like blast the hill out or use bulldozers to bulldoze it. And so you get this nice road cut. And so a lot of geologists will spend their time on the sides of highways. And you can see a lot of these on your way up into Oklahoma through the hills up near Wichita Falls and all that stuff. One place close, you don't get to see anything super, super interesting, but if you take, I think it's 1382 out towards Joe Pool Lake and Cedar Hill, there's one big hill that's just like all limestone layers. And there's not really any place for you to stop anymore. And in fact, I think they tell you not to stop because rocks fall from there all the time. But it's a good like 20 or 30 feet of like a straight cliff face. That probably has at least some interesting limestone formations in it. Nothing folded or anything like that. But so the point is, before I get too distracted, is deformation happens. All change in shape, position, or orientation of a rock mass is called deformation. So doesn't necessarily have to break or bend. Just if it gets moved in some way, that's going to be deformation. Bending and breaking occurs when stress exceeds the strength of the rock. And so there's always some sort of stress on it, but if it's more than the rock can handle, you will get some sort of bending or breaking. The bending is going to be called elastic deformation, and that kind of makes sense. We have elastic deformation versus brittle deformation, and so that's what they have here. Ductile or brittle deformation occurs when elastic limit is surpassed. The elastic one is going to be ductile. You're going to have some sort of movement without really breaking here. Rocks return to their original size and shape when the stress is removed. Not always. If you have a layer that's pushed like this and you get the fold, when the stress is removed, they're not going to like unfold and go flat again. So in a single small piece of rock, you might have it return back to its original shape, but generally not when you have the full folds like that. And the strength of a rock internally is influenced by its temperature. If it's hotter, it's going to be less strong. By its confining pressure, the rock type, and the time frame that the stress is applied over. If it's a short time frame and it's high stress, it's probably going to break. If it's kind of a gradual stress over a long time, it's more likely to bend instead of break. So these are your two different types of deformation: brittle deformation and ductile deformation. Brittle is going to be your rock breaking. It's going to result in fractures and faults similar to these blocks. Sorry, I guess the online people are probably like, I can't see the blocks. Brittle is going to be fractures and faults similar to these blocks, where ductile is going to be your bending and folding similar to your styrofoam plates. All right, folds, wave-like undulations. We know what folds are. They're when your rocks fold. When they bend under compression, compressional forces result in shortening and thickening of the crust. Know that if I pull these apart, nothing happens. And so when we talk about folds, it's always because of compression, because you're squeezing things together. Come on. You're squeezing things together on either side. We have lots of different names for folds. To be fair, there's generally just two ones, anticlines and synclines, and then we have four different terms that kind of describe the anticlines and synclines. And you can see these all over the place. It just depends on where you go. So anticlines and synclines, how do we know the difference between these? This is probably really, really dumb, but it's always helped me remember it, and so I really, really like it. An anticline is going to point upwards. And so if it points upwards, most people's aunties are very nice ladies, and they will go upwards to heaven when they leave this bodily earth. And the opposite, synclines, if someone is a sinner, they will go down to hell, and that's why synclines point downwards. Very, very dumb. Most geologists would probably be mad at me for saying that, but I've always remembered it, and it's an easy way to remember it. So anticlines point up towards heaven. Come on. And synclines point down towards the bad place. And that's the way I've always remembered it. A couple things to point out, because I believe they will even ask questions about this. But in this layer structure, which one's the oldest and which one's the youngest? Top one's the youngest, the bottom one's the oldest. So when you have an anticline, note that the older rocks are in the center and the younger rocks are on the outside. And so no matter which way you fold this, that is also going to be helpful, because when we get to like overturned ones, you can have an anticline that gets overturned. Once it gets overturned, it looks like a syncline, but if you date the rocks and see that the older rocks are on the inside, the younger rocks are on the outside, you know that it's an overturned anticline and not a regular syncline. And so it's less about the direction that it points. If it doesn't get overturned, you can just use the direction. But it's more about the age of the rocks. So if I go the other way and do a syncline, the younger layer that's on top is going to end up in the middle, and the older layer that's on the bottom is going to end up on the outside. And then if I flip that over, the ages still stay the same, but now it's pointed in a different direction. Or even if it's just turned on its side, now I don't know if it's an anticline or syncline. If it's older in the middle and younger on the outside, it's an anticline. If it's younger in the middle and older on the outside, it's a syncline. Now, we have a couple different ways to describe these. You can have symmetrical anticlines and synclines, which basically they're symmetrical. They look the same on both sides. They're going to have similar angles, similar lengths, everything. Asymmetrical, your limbs are going to be different. So it's going to be more like that kind of thing. So like a short, sharp bend on one side, a gradual kind of long bend on the other side. That would be more asymmetrical. And then overturned is obviously overturned. You can have it on its side. You can have it flipped all the way over. It can be pretty much anything. And then recumbent, your axis is going to be horizontal. So you have your fold like this, but it's actually turned like that, where your axis is horizontal. Oh, like this. So your axis is going to be horizontal, that's recumbent. So your axis would go in and out like this, that would be horizontal. Which, to be fair, oh no, wait, my bad. Your axis is going to be your symmetrical line. So it's going to be like this. That would be your horizontal axis. Okay. So I want to block out the screen for the online people. They're probably going to show us some images, even though we just kind of went through it. Two more things. I forgot about domes and basins. Domes and basins are more 3D. So let me grab a stack of papers. Instead of, hello. Yeah. We're going through folding of rocks. So
Folding of rocks.
Yes. So instead of having just your regular fold, anticline, or your downward fold, syncline, you actually get the 3D fold, which is basins or domes. So obviously a dome is going to be upward. A basin is going to be like a bowl where it's pointed downward. And so it's just a little bit more 3D. If you're only looking at it from the side, you may not be able to tell the difference. It's either just going to look like a regular anticline or a syncline. But if you get to see it over a certain distance, you might be able to see that it's a bowl. And then this, it's not very big. They might show one on the next page. They don't. But you can see on your slides, you can kind of blow it up a little bit. They have these nice 3D kind of blocks that show you what it would look like from the surface, because generally we don't get that slice down into the subsurface. We have to look at it from the surface. And so like here, you can see on the surface, you only get to see the top part that's curving around here. You only get to see it come around. You don't get to see which direction it's headed. And so what we would actually do in field camp, because you only get to see like the changes in the lines, is we would come in with a geologist compass. And so it has a normal compass on it. It also has like a level that you can turn, and a flat side on the compass. And you would go into the transition, which is not the right word, but it works. The transition from one rock to another, and you find like a flat spot on the rock, and you put your compass on there, and you can actually measure the angle that the rock is kind of headed down into the subsurface. So you get somewhat of an idea of what it's doing down there and what it should look like underneath. So this one, I don't know if this is a full dome. What I think this is, that's obviously a dome or a basin. And you just have to look, is the oldest stuff in the middle? If the oldest stuff is in the middle, that would be a dome with like the top sliced off. So your old stuff is coming up from the bottom in the middle. If your youngest stuff is in the middle, that would be like a basin with the top sliced off. So your youngest stuff is pushed down into the middle. What this one I think is probably like a inclined anticline or syncline. So it's folded like this, and then it's tilted down, and then the top gets eroded away. So you kind of get this horseshoe shape of the fold exposed to the surface. Although they have it in the picture with the domes and basins, so maybe I'm wrong. Maybe I'm wrong there. Now, usually you don't just get one of these. It's a long chain of things that kind of happen as your compression happens. You get all sorts of little bending and folding events. So here you have your anticline followed by a syncline, followed by another anticline, which is kind of asymmetrical and turned over a little bit, followed by another syncline, and then an even more asymmetrical anticline with a little bit of an overturned limb. This isn't the greatest projector, so you can't super see it, but all sorts of little things here. And this is actually what we did in that trip to Oklahoma. We went along the roadway, and these anticlines are so big, you don't really get to see them. But at one outcrop, you would stop like right here, and you would see that they're headed down this way. You'd go a couple miles down the road, stop at another one, see that it's headed that way. You go even further, and you kind of build this little picture along the highway. And then when you go back to school, you kind of interpret what you think is happening, whether they're anticlines or synclines, based on the age and the pattern that you saw. Okay, now moving away from folds and getting into faults. So I'm gonna put my paper and my foam away, and now we're gonna get into some faults. We got a couple of different terms for faults, and I'm gonna introduce first the hanging wall and the foot wall. And there's a great way to memorize this. And turn the lights on. I'm taking this over here because this has always helped me too. This is extremely stupid, like the other thing, but sometimes it's the funny, stupid things that help you remember stuff. Let's see. So we're always going to have this kind of image here, and y'all can see that with this. You start off with a block. That's normal. And then you put a fault in it. Either way, you put a fault in it. So you start off with your normal block, and you put a fault in it. Now, we have two different shapes of block here. And this is very idealized. It never really looks like this in real life, but the idealized versions help us visualize things. So when you see the weird stuff in real life, you can match it up. So we have a block that looks like this, and we have a block that looks like this. Now, it's going to be really, really dumb, but it should help you out a little bit. Man, this is bad. What is that? It's a shoe. It's a shoe. It looks like a shoe. It looks like a kid drew a shoe. There's the laces, and there's where you put your foot in, and you can even like put a sole at the bottom. But this is a shoe, and the shoe has toes, and this is a shoe. So this is going to be the foot wall. That's the way I remember it. So the one that looks like a shoe is a foot wall. And this one is called the hanging wall. And you could easily be like the one that has the toe at the bottom or goes down underneath is the foot wall. And the one that goes above is the hanging wall. But if you imagine the shoe, it's a little bit easier, at least for me. And then the hanging wall, I always imagined like a guy hanging off like a cliff climber, a rock climber, not a cliff climber, that's not what they're called. You have like a rock climber hanging off the cliff here in dramatic fashion. And so that's how I remember foot wall and hanging wall. You've got a foot wall that looks like a shoe or a foot. You have a hanging wall that has like a little person hanging off the edge of it. And this kind of helps you memorize which one's which and what they're going to do. Because with the hanging wall, it's always normal for the hanging wall for the guy to fall, right? He can only hang there for so long. You can't just hang there forever. At some point in time, you've got to come down. And, let's be honest. Some people can do pull-ups. Most of us, if we're hanging on to like a rock cliff, we're not going to be able to pull ourselves up. We're just hanging there, hoping that somebody comes and rescues us. But this guy, no one's coming to rescue him, and eventually he's going to fall. Good news is it's only like a 6-foot fall. He's going to be fine. Maybe he sprains his ankle. It's not like a life-threatening fall. But at some point in time, he's going to fall. And so that's normal. It's normal for the hanging guy to fall down. And so if your hanging wall goes down and your foot wall comes up, that is a normal fall. And the other way to remember that is if your hanging wall goes down, your foot wall comes up, that's extension. I've pulled them apart. And that is what happens normally all over the planet. Things are separating. Gravity wants to pull things down. Extension is much, much more common than compression. So that's why it's called a normal fall. Not because it's normal for the hanging guy to fall down. But that's the way I remember it. So extension is normal. Your hanging wall goes down. Your foot wall doesn't necessarily come up, but it does come up sometimes. But normally foot wall stays there. Your hanging wall falls down. Everybody sees hanging wall falls down. That's normal. The opposite side is going to be that your hanging wall goes up and your foot wall comes down. That's what we call reverse. That is a reverse fault. So normal fault versus reverse fault. And reverse faults are going to be compressional. So if I squeeze this together, they're going to slide up like that. I'm going to have compressional. I'm going to have this overhang up top. I can't point at it if I'm holding both of them. I'm gonna have this overhang here, and that's gonna erode away pretty quickly. Usually that doesn't stay like that for very long, just because of erosion and gravity. So let me add that over here. Reverse is compressional, and then normal is extensional. Nice. Okay, and that should help us remember some of this stuff. Now let's go back to the PowerPoint. So they've given us a little bit. Hanging wall, footwall. They're going to introduce dip slip faults, and the dip, we're not going to do too much with this, but know that the dip is just the downhill direction on a fault. So I have a fault here. This is the dip, heading down that way. Whichever way water would roll or a ball, if you set this on here, would roll down, that's going to be the dip. And so if I move in that direction or even reverse, that is a dip slip fault. Versus the strike is a horizontal plane on the fault. So, and actually strike is something, if you go hiking very often, especially in the mountains, or using maps to kind of hike around instead of just like wandering through the woods. Let's say you have a hill. This isn't a great hill, but let's say you have like a hill or a mountain, and you want to get from this side to that side. You can go over. That's going to be a lot of work. You'll have a nice view at the top, but it's going to be a lot of work. If you just want to get there without getting like super tired because you still have a long way to go, the best way to do is head around or strike out. Head around the strike. Just stay horizontal. Don't walk up. Don't walk down. Just literally walk at the same elevation around the outside of the hill or mountain, and you'll get to the other side and still be able to have a lot more hiking left in you. So dip slip faults are going to move up or down. Strike slip faults, which we'll see on the next page, I hope, are just going to move horizontal left and right without really changing elevation. The fault scarp is basically exposed fault. So where I have a normal fault, the part of the fault that's now exposed is called a scarp. Are you paying attention at all? Were you looking at your PowerPoints?
Yeah.
Did Mr. Warner catch you looking at a different page?
No.
Okay. Hope you
I'm on the
did.
same PowerPoint.
I'll hear about it. Good. And then if it comes up, I've got exposed fault over here, so that's going to be your fault scarp. Now, let's see. They show you some fault scarp here. And actually, fault scarps are what I looked at in my my master's thesis, which I don't know if I left a master's thesis over there, if I took it back home. But yeah, here's a hanging wall block. Here's a footwall block. And actually this one, you see this fault on the other side. It looks like they have this middle section here with the hanging wall on both sides of this little middle section. And I can't tell if it's gone up or down. Oh yeah, you can. See it? This red layer right here stops and starts up over here. So this hanging wall has actually gone down a little bit, just like that. Wonderful. And then obviously once it goes down, it fills in with sediment in between, which kind of levels everything off. So wonderful. So they introduced normal faults, which I've already talked about. In a normal fault, your hanging wall moves downward. That's because you have extension. They have fault block mountains, which are caused by these. Let's see. Yes. Horsts and grabens, which are obviously Nordic terms from the Scandinavian peninsula. But grabens will be the ones that drop down. So if I have that kind of thing happen, that's a graben. And then horsts will be things that have kind of been pushed up. And so I don't have any fancy dumb things to help you remember that. But grabens go down, horsts come up. Do they show you this? Yeah, here you go. So these are going to be your grabens that have kind of fallen down. I don't know that necessarily. Oh, yeah, there's a horse. This one's kind of raised up above everything else. They have it in light letters here. So horses are up top, grabens are down bottom, and there's an actual picture of your horse and graben. So if you see the rocks themselves, you can kind of get the idea of the faults and the different ages. But from the surface, it just kind of looks like mountains because everything's been eroded away. But if you spend a couple days, couple weeks, kind of exploring the geology and taking notes and writing things down, you can get to the right conclusions. So they talk about reverse faults. Reverse faults, your hanging wall moves up because you have compression. If it's at an extreme angle, so instead of this, if your angle is more like closer to horizontal, this is not good with the blocks, but it will be called a thrust fault because you're thrusting a piece up over top of another one. Both of those are strike slip faults. We haven't got to wait, no. Both of those are not strike slip faults. I'm sorry. Reverse faults are still dip slip faults. They talk about the dip here. A strike slip fault is essentially like a transform fault in plate tectonics. You're not going to have anything up and down. It's only horizontal displacement. And like I said, parallel to the strike, which is your horizontal direction. So here's some images. This is a normal fault. You can see that the block that came up here is eroded away and showing your mountains here. Here is a reverse fault, same erosion. In fact, they don't look too different from the surface. You'd actually have to do a little bit of aging on these layers to try to figure out whether it was a reverse or a normal fault. If you can see any evidence of the fault line itself, that might help out a little bit. And then if it's a reverse fault, but it's a little bit more inclined, the angle of the fault plane is a little bit more inclined, that will give you your thrust fault. And then here, no up and down, no mountain building or anything like that, just sliding side to side. This is your strike slip fault. And you can see the river has been offset where it used to come straight across. Now it's moved over. And they do have terms for whether they're normal or reverse on a strike slip fault, but I don't remember off the top of my head. Basically, it's whether it's going left or right, depending on which side of the thing you're standing on. So like this one, it doesn't matter what side you stand on. If I'm standing on this side, the block opposite of me has moved to the right. If I'm standing on this side facing that way, it's the same thing. It's moved to the right. And so whether the thing that you're looking at has moved to the right or left is how you identify which way the strike slip fault goes. Now, last couple slides, orogenesis. Orogenesis is mountain building, how we build our mountains, how that kind of thing happens. So your older mountain chains are eroded and less topographically prominent. These are going to be your mountains in Oklahoma. Oklahoma has lots of old mountains. They're just like big hills now. They're not much of mountains because they're extremely old and they've all been worn away. To be fair, they probably weren't super huge to begin with, but definitely a lot smaller than they are now, which is also why Oklahoma has a lot more tectonic activity than we do, because those old mountains still have old fault lines that kind of helped, were part of their creation. They still have some stuff going on there where we really don't have any of that. We're just super flat. Most mountains are going to be because of collision events or compressional events. So you have compressional mountains, large quantities of pre-existing sedimentary and crystalline rocks that have been faulted and folded. Let's see. Yeah, here we go. This shows you some old mountain belts, some young mountain belts, some shields. Shields are going to basically be like the original super oldest continent, part of the continent. And so if you go to the shield, you're probably not going to see a whole lot of mountains, and you're going to be able to find the oldest rocks that you can find on that continent, period. So young mountains in the United States are going to be your Rocky Mountains in the West Coast and your Cascade Mountains on the like Pacific Northwest. Your old mountain belts are going to be like the Appalachians. The Appalachians have been around for a long time. They're still pretty impressive mountains, but they're not anything like the Rockies or anything like that. Almost all of the tallest peaks in North America are in this mountain chain from the Rockies that pretty much goes all the way up. But the Appalachians still have some good mountains and hills going on over there. And then the shield, the original part of the North American continent is up in Canada. That's kind of like the basis for which everything else has been added on to. And then you have some stable platform, shields covered by sedimentary rock. So still part of most of the original stuff, but kind of covered up. You don't have exposed rock. That's like the original rock. You'd have to dig down to see it. So yeah, some new mountain belts all through here, old mountain belts, and I think they talked about the mountains and plate tectonics, and you can see that you have your mountain belts here, the Caledonian Mountains up here in Greenland, and then this is the Atlas Mountains are younger. So interesting because they kind of implied differently in a different slide. I'd like to look at that. But yeah, some old mountains, some new mountains, wonderful. So how do we get mountain building? You have subduction of oceanic lithosphere is the driving force for orogenesis. And basically what happens, if you think of this almost like Japan or Hawaii, as your oceanic lithosphere gets subducted, these, not only is this going to build up new land, so you're going to have volcanoes that come and kind of build these islands, but eventually this oceanic plate is going to be subducted somewhere. They said none of the oceanic plate is more than like 200 million years old. So it's all relatively young. It gets recycled a lot. And when this plate gets subducted underneath something else, essentially, this is maybe a bad image, but you know how you like scrape mud off your boots? That's essentially kind of what happens to the islands or any larger piece of land that's not necessarily a continent. When the oceanic plate gets subducted underneath, that island gets like scraped away and gets plastered onto the edge of the continent. And so we can actually go and see the ages of rocks and see where all that has happened. And what we call that is an accretionary wedge. So any kind of material added on as it's kind of scraped in, you can see from my arms a little bit that it would be almost wedge shaped, everything that just gets piled up in there. So that's your accretionary wedge that helps add new rocks to the edge of the continent. So here's an example, not really with the islands, but you can see you have a passive margin, not really any mountain building going on. You start to subduct oceanic plate. As the oceanic plate happens, you get volcanoes that come up and you start to build your mountains. This would be like your Cascade Mountains up in Washington, Oregon, the western end of Canada. And then eventually they've got a little bit of it happening here. Your sediments that are coming off the ocean just kind of get scraped off at the edge of this continent and start to build this wedge right here. There's not really anything there to begin with. And then you start to build up that wedge, and if you build up enough of it, it can kind of add new land to your continent. So you get a new little area there. Yeah, here's the island chain that kind of gets scraped off. So here's your island out in the ocean, possibly formed from some other sort of volcanic source that's now gone. As the plate gets subducted underneath, the plate itself will sink, but these rocks are going to get scraped off on the edge of the continent. So as it goes, the first set gets scraped off here. The second set comes in further. It gets scraped off. And really only the oceanic plate is the plate that gets subducted. So this would be like India and its collision with the Himalayas. It wasn't like a huge piece of continent. And it went up. The continental or the oceanic plate subducted, but India stayed up, which I think is the end. All right, nice. This last one is just continental, and we've talked about that a lot. Two continents smashed together. One of them is going to go up, and you're going to get your big mountains happening. So, wonderful. We finished. Proud of y'all. Proud of y'all.
What is that ocean floor like? Or the fault?
What do you mean, what is it? Oh, wait.
The plate lab, the packet.
That's the one I gave y'all. Wait, what are you asking about? What's your question? Oh, when is it due? I haven't set a due date yet because I know not everybody's really started on it, and because I haven't put it online for the online people yet. I did print out a better version. If you've started on it, you can just copy your answers over. It's the exact same thing. But the pictures are a lot better on this one than the other one. So yeah. You should be able to see some better stuff on it. So as soon as I get it up for the online people, I will kind of start the clock on that. But we're slowing down the lab, so it's not going to be big. All right.
So funny.